of E dot dt, which is the flux, well, the flux times n divided by times n, or this divided, that integral divided by n will be the flux, the change in flux. And so you start with zero flux, you reach a maximum flux, and then that maximum goes back to zero. So the change in flux on one side has to be equal to the change in flux on the other side, unless you don't start at zero. But even with the magnet in the thing, some of you were finding they were equal. And so this results from a change in magnetic field. And so the magnetic field goes, so the flux goes from, flux, the final flux will be the maximum flux, and the initial flux is zero. Or you go from in the opposite direction when you fall out. And so the maximum flux is related to the maximum field this way. And since everything, the coil and the magnet are lined up in the same direction, we ignored that. It's just 0 or 180, so it's 1 or negative 1. And so the change in flux, which is the area under the curve, divided by n. From that we can get the field. We just have to divide this by the area. But you might make the mistake of using the area of the coil, whereas you should use the area of the magnet. And you might ask me, well, why is that? Because if we tilt this up so that we see the coil, and we see the magnet, I look here and I see the magnet coming down. Well, the only place there are flux lines are inside the magnet. There's no flux out here. So the flux, which we found, is B times A. And so we want to get B, we have to know A. So why don't we use this A? Because there's no flux out there. The flux is just in the magnet. Right? The magnet is like this, and the field lines come out, and then they do this. Right? But we're ignoring that effect. And even if you ignore that, some of them, there's going to be a few like that. We're just ignoring the fact that there's a little bit of that. So just to keep it simple, we're thinking of the flux this way. So the area that you want to use to get the field is the area of the whole face of the magnet. And that's the reason. I don't know if that was it.
It answered part of my question. Then the other half was, so we're using the area as the total change in magnetic flux, the area under the curve, I mean. But are we using like the sum total of both peaks, or just one area under one peak?
I don't think you use the peaks at all, do you?
There was definitely an equation that was area under the curve divided by like area of the whole face times.
This is area of the graph on the lab report.
Yeah, well, the area of the graph you got using the...
Yeah.
In the past, we didn't have that tool when we were using a different thing. It didn't have the tool. And so how do we get the area? I think we just estimated it by taking this. We treated it like a triangle. And we just took the height times the width and divided by 2. And we get an estimate of the area. But now we have the tool. It gives us the exact area.
Yeah, I think she's asking though, like, are we gonna use area just that one? The one
Well, it's the same.
Yes, so you're not doubling it, you're just.
No, no, no.
Yeah.
No, what's the total area on the curve? Zero, because it starts with a flux of zero and it ends with a flux
Yeah.
of zero. So if you take this time interval,
It was zero.
the change in flux is zero, because the difference between zero minus zero is zero. So you're just taking one of the areas.
Is the lab due Monday, at 1:59 or 11:59?
Oh, I'll change that.
Okay, it's supposed to be 11.
It's supposed to be 11. Remind me at the end of class, I don't want to take the time to do it now, and make that change. Or send me an email if you see that it's not changed. No, I do mean it to be 11, and I just push the assignment in the lab till Monday. You should finish them, I mean, it's up to you, the quiz is Monday. Part of the reason I did that is